Today we're going to be talking about Retrieval Augmented Generation, or RAG for short. I'll be explaining some of the differences in output available to us when talking with a large language model. And finally, I'll be showing an example of a simple RAG application for extracting key information from a publicly available PDF statement, all running locally on my machine. If you'd like to skip the introductory part of this video where I give a high-level overview of what a RAG AI application looks like, please feel free to skip ahead using the chapter timestamps in the video description. I should mention this is a really simple local deployment of some RAG concepts with a structured data output, and this video is meant for complete beginners to RAG concepts. There are a lot of video demos out there about how to deploy RAG agents on a larger scale, which is something I'd like to tackle in the future. I'd also like to thank YouTube creator Pixagami for sharing his RAG projects, as much of the code structure in this demo is based on his work on various Ollama RAG projects. Please check out his channel linked in the description if you'd like to see more. So before we get started, let's refresh ourselves on what a RAG application is and how it works. Retrieval Augmented Generation is an AI technique that enhances the capabilities of LLMs by integrating information retrieval with text generation. RAG allows an AI model to fetch relevant information from a knowledge source external to the model and incorporate it into its response. In our case, that will be in the form of a vector database with embedded knowledge. Some of the most popular use cases for RAG include customer support chatbots, employee knowledge access, personalized marketing, or like the use case in this demo, text retrieval. Now to spin up a RAG application, we first import and embed the data into a vector database. We ask the LLM a question using a custom prompt and the context provided in the vector database. And finally, we parse the query response and store the output as we desire. I should mention, vector databases are specialized databases that can be used for similarity search, enabling them to efficiently find data points that closely match a given query vector. Using linear algebra, an embedding model can ingest chunks of knowledge data and assign each chunk to a vector. This embedding can later be picked up by a general large language model as context to assist in answering a user's query. Let's take a closer look at the first step of our RAG application, vector database embedding. First, we extract the text data from our knowledge source, normalize it, and tokenize it for model use. Then we chunk the data, breaking down our documents or data sets into smaller, manageable pieces like paragraphs, sentences, or fixed-size tokens. Next, we embed the data by converting text chunks into numerical vectors using a pre-trained embedding model. Finally, we store the embeddings in a vector database for efficient similarity searches with metadata linking back to the original text. Once we've created our vector database, we can go a step further and ask the LLM a question about the embedded data. We start by providing the application with a natural language query. Just like the initial knowledge embedding on the last slide, our custom query is also passed through our specialized embedding model, which generates a vector representation that captures the semantic meaning of the text. This helps us perform a similarity search in our vector database. The retriever function searches for pertinent information related to the query, and then that information is combined with the original natural language query. This combined input is fed into a general large language model, which generates a response that incorporates both the retrieved information and its own knowledge. Finally, we parse the LLM's response as we desire to get our final response. We can read the final response from our command line interface, pass it to a user interface, or store it in whatever data structure we prefer, be that SQL database, CSV file, Excel, data lake, etc. And before we go any further, I'd like to take a quick detour to talk about structured versus unstructured data outputs. This is a key part of the functionality in our use case, so it'll be helpful for us to review. Okay, so here's an example of an unstructured data output from our LLM. I'm running this on a Jupyter notebook in VS Code, which gives us some flexibility to chunk code and use some markup in individual cells and store for later. I'm also running Ollama on my local GPU rather than in a cloud environment. We'll be talking more about Ollama later. So in this example, we're talking directly with the pre-trained LLM without using any special RAG embedded vector queries. There's no vector database in the background here provided to the LLM as context. This is just a one-on-one conversation with the LLM. So we give the LLM, which is in this case Mistral, a couple sentences as some context and ask the LLM a question about the context. So for context, we said, I have 2 pets, a cat named Luna who is 5 years old and loves playing with yarn. She has gray fur. I also have a 2-year-old black cat named Loki who loves tennis balls. And then for the question, we said, can you tell me more about my pets? So as you see, when we print the response, the LLM returns a string of metadata, including the natural language response. But we can also just print the natural language response by using the response.message.content syntax. And so this is kind of more like if you were to use some of the popular closed models like ChatGPT or Microsoft Copilot, you'd typically get a response like this back in the user interface. This is just a parsed version of the response that we're doing in the print above. So this works well if we want to have a natural language conversation with the LLM, but what if we want to assign some of this information for use elsewhere? So rather than getting a sentence back from our query, perhaps we want to store some of the information in the response for computation or a dynamic variable assignment. And that's where the structured data outputs come in handy. So we can instead ask the LLM to work with Pydantic, which is a Python library for data parsing and validation. It helps manage some of the regular expressions and can work hand in glove with Ollama locally to assign response parameters to returnable class objects in the LLM's output. So in this code, we create a class called pet, which inherits from Pydantic base model. We structure this class as name, animal, age, color, favorite toy. And then we create a pet list as a placeholder to kind of act as a list of all of the classes of pets involved. That way we can dynamically assign any pets that are returned in this this query without having to specify how many pets there are, and just do it as an entire list. So we combine the context and the question together and ask Ollama to run the Mistral model with a formatted output of this pet list.model validate JSON. And then we're using the same syntax from before, which is taking the natural language output of that, not returning the metadata to us. And this time, when we run the code and print the assigned variable pets, we get a structured output in a JSON format with each of the class attributes: name, animal, age, color, and favorite toy listed. We'll see this can be a very useful enhancement to our interaction with the LLM later when we extract data from a PDF file. So moving on, now that we've seen what RAG application is and what a structured data output looks like, let's take a look at a practical example. Recall we will, number 1, begin by importing and embedding the data into a vector database. 2, we ask the LLM a question using the context in the vector database alongside our custom prompt. And 3, parse the response and store the output as we prefer. All right, so in this example, we'll be taking a look at a publicly available excerpt of a PDF portfolio statement for this Clark County Bond Funds. This is a text-based PDF, which means you can highlight and copy and paste text from it, which is in contrast with a scanned PDF, which would require some specialized optical character recognition or OCR software to read. You can see that this document contains a list of money markets with a QSIP label, as well as a par market book value label for each one of these. So our task will be to extract each of the positions from this file so that we can examine the QSIP and par value of each of the positions mentioned. So to do this, I set up a project folder with the codebase and the PDF file for the RAG application consume. I've stored this Clark County Bond Funds PDF in this data folder here. I've also downloaded the necessary libraries and Llama onto my machine, along with the embedding and general models we'll be using. But these are all free and open source for anyone to pick up. I'll be running this dedicated embedding model called Embed and a partially open source 7 billion parameter chat model called Mistral, both running on an Llama environment locally. Llama is an open source environment designed for running LLMs on local GPUs rather than in the cloud. It also has some dedicated Python toolkits that are helpful in interacting with the models. So we'll be running this entirely on my local machine with an NVIDIA 4070 Ti Super rather than in the cloud. If we want, we can take a look at the models that are available to us on Llama. You'll see there's a huge variety of general models, embedding models, and even some more specialized ones that are available to download and host locally. So let's take a look at the populate database module. First, we import our dependencies that we've already downloaded. We have Parse, which helps us if we want to run this code by command line interface, OS for navigating folders in our operating system, and Shuttle to assist in clearing the database folder if we run this repeatedly. We also are importing ChromaDB, which is the vector database, which we'll be using to store our data chunks. We're also loading PyPDF library and a few libraries from LangChain, which are a helpful set of tools for interacting with machine learning and AI. You should also notice that we're getting the embedding function separately. We're calling this from a separate .py script in the project folder so that we can change this on the fly if we determine that the embedding results are insufficient for our purposes. So in this case, like I mentioned, we're using the nomic embed text large language model, but if we wanted to, we could switch this by commenting these out and restoring this code instead. We could instead use the AWS Bedrock embeddings model. It would just require us to connect to the AWS API with our AWS IAM credentials and assign this API connection as our desired embedding function. Going back to the populate database script, we have a main function which has several nested functions within it. The first chunk of code helps us use the argparse functionality, so we can run it by command line if we prefer. This allows us to reset the database by calling the clear database function we've defined below. The main function then loads the documents, splits them into chunks, and takes those chunks and adds them to our ChromaDB vector database. So if we dig into these functions, the load documents function uses the PyPDF function and passes the data path folder we've defined as the data subfolder from our project folder earlier in the code. Our split documents function calls the recursive character text splitter and passes some chunk size and chunk overlap arguments to it. And then the add to chroma function opens up a connection to a new ChromaDB vector database adds or updates new documents, and assigns each chunk some source metadata about the text. Once we populate the database, we can go back into the project folder and see it's created a new ChromaDB vector database for us with the embedded statement. Now that it's embedded, we can move forward and pass a query to our general model using our embedded PDF statement as context. We go back to our Jupyter notebook, which is where I'm storing the query rag function. In this code, we import a few functions from LangChain and import the Ollama library here to interface directly with the local Ollama environment running on my GPU. We also import the same get embedding function we defined earlier and the pydantic base model we used in our pets example about structured data earlier in this video. Just like in our pets example, we create a class structure for Ollama to be able to assign values to the query results. In this case, I defined QSIP and QSIP list since we want to extract every QSIP from the document. I'll also ask the model to return par value and par from this document, although this is probably overkill, since as we'll see, asking the model to return par alone seems to be sufficient. When we run the code, the query rag function combines the context and the question, initially stored as query text here, into a single prompt for the LLM. The function searches our ChromaDB instance using a similarity search and returns the results. We use the Ollama chat module to talk with our general LLM, Mistral, and ask the model to return the results in a JSON format. This way we're getting each QSIP and par value back from the LLM in a structured data output rather than in a natural language output. We print the results and get a list of every QSIP in the table with a par value for each. This is a pretty good result, but we can take it a step further and put this into a data table so that we're not restating the QSIP and the par value names for every observation. So we import pandas, which is a popular computational Python library, kind of like Excel. We stretch our QSIP and par data into an array and then pass that array into a pandas data frame, which looks like this. So if you check any of these, you'll see it lining up with the QSIP and par values we've returned via the RAG application compared to the PDF statement. The result looks kind of similar to a table in Excel, but we can even pass it to an Excel file if we want. So as you can see, we created an Excel file in the project folder with a static name, but we could also do that dynamically if we wanted. I don't have Excel on this machine, so I won't be able to show you, but pandas can pretty much create any output we'd prefer to use to store the data, whether that's an Excel file like this, a CSV file, entries in a SQL database, etc. So now we have a completely structured list of all the returned QSIPs stored and ready for us to use in our daily work. So that concludes my demo for today. Like I mentioned at the beginning of the video, this is meant for folks that are completely new to RAG concepts and not a large-scale deployment. If you have any questions or if you like what you saw, please leave a comment below. Thanks.